So we talked about high ground, contour lines, spot heights, visual things you could see on a chart, motorways, towns, railways, um, airports, um, and we've talked about restricted areas, prohibited areas, and danger areas. So we're going to talk now about navigational aids that you see on the chart. Obviously, you don't see them on the ground so easily, but you see them on the chart. Now, navigational aids are two different sorts of navigational aids. Now, I am going to cover this in much more depth. Oh, excuse me. Oh. Nearer the end of the course. But navigational aids that we generally use for PPL consists of two things. One is what's called a non-directional beacon. And in the cockpit, we have an instrument called an ADF, which is an automatic direction finder. And what the ADF does is it's a needle, and it just simply points to the beacon. And this is the ADF in the aircraft. So you can see it's just a circular instrument, and it just has a yellow needle that points the beacon. And in this radio stack, in the middle, we actually have a receiver that we can tune in the frequency of that beacon and make it point to it. So just I'll just show you what that looks like on the chart. I'll just zoom into one. So there's Woodley 352. Which is here. There we go. Let's just bring it up. There we go. That's what they look like. It's just a circle with lots of dots around it. You can see three dotted rings around it, with a dot in the middle of it showing where the actual NDB is itself. And you can tell because it's got WOD and 352. 352 being the frequency, and WOD, Whiskey Oscar Delta, being the Morse code it transmits, so you know what beacon it is you're looking at. So the other type of beacon we get, navigational aid on the chart, is what's called a VOR, and that's a hexagon that looks like this. VOR, VHF omnidirectional radio system, and the VOR is a very similar thing to an NDB. It has a frequency next to it on the chart, and it has what's called its ident. And in the cockpit of the aircraft, you've got a receiver that looks a bit like that, or looks a bit like that. And once again, you've got one of the radios in the radio stack in the middle as a facility where you can put the frequency in, and this will show you where that particular VOR is, and some VORs it will also show you how far away it is as well. So we'll find a good one of those on the chart. And a typical one of those would be the Compton VOR, for example, Charlie Papa Tango, which is just over here. It's up here somewhere. Okay, well here's the Daventry VOR. So this is what it looks like. So can you see how the VOR is quite a lot different? Is that we've got this hexagon that we discussed with a dot in the middle of it, and you'll notice that this has got a compass rose around it. Now the reason it's got a compass rose around it is because unlike the NDB, which just has a needle pointing to it, on a VOR we can actually select a certain position on this compass rose that we want to. I'm going to discuss this a lot more later on in the course, but at the moment I'm just pointing out where these are. So once again, this is the frequency it transmits on. This is the ident, Delta Tango Yankee, and DME means distance measuring equipment. So this, as well as being a VOR, this can also tell us how far away we are from the VOR. And all on the chart, you'll see that there's all over the chart, there's VORs, NDBs, and navigational aids sprinkled all around the chart. Now, the next thing we need to talk about is airspace.
Hey, Paul, is the NDB and the ADF, do they have the same icon?
Sorry?
Do the NDB and the ADF have the same icon?
Yeah, the NDB is what's on the map, the non-directional beacon, and the equipment in the aeroplane that receives it is called an automatic direction finder. So ADF is in the plane, NDB is what's on the ground. And once again, the VOR is on the ground, the VOR receiver is the bit that's in the aircraft. So, but generally we combine them and we call them sort of NDB, ADF, VOR. Yeah.
What does VOR stand for again, please, Paul?
VHF omnidirectional receiver.
That's a hard one to remember.
But don't worry about it at the moment. We're going to talk about it in a lot more depth We're going to spend about an hour discussing it later on in the course. So at the moment, I'm just pointing out these things on the map. So let's move on to airspace. So how many different classes of airspace are there? What do you reckon, Vinny? You've done air law.
So I was just trying to count on my fingers.
Right, well, what do they go from? They go A, B,
B, C, D, E, F, and G.
Okay, so these are the different sorts of airspace you can get. Class A, B, C, D, E, F, and G. Now, each class of airspace has different set of rules relating to whether you can fly in them or not, and each of the rules stipulate things like, for example, in Class G is what we call open FIR. You can more or less do what you like. When you're in Class D, for example, you can still do a reasonable amount of what you want, but you must be in contact on the radio with the controlling authority. Things like Class A and B, IFR and VFR are separated, and you've got to get a clearance for everything you want to do. And each of these has a different, you can do different things in. What exactly you can do is not part of navigation. That's all covered in air law. But let's look at the map and see if we could find some of these different classes of airspace. So can you see the map has got lots of purple lines on it all over the place? Now these purple lines, these straight lines, are all the different airspaces boundaries on the map. So let's just see if we can find a few, shall we, that we can zoom in on. Well, here's some over the top of Swindon. So you'll notice that this big square here, this big rectangle, sorry, is Class A airspace from flight level 6.5 and upwards. And in actual fact, you'll notice, can you see there's like a big, long, straight thing that heads off here? In fact, that's the airway that heads off to America. That's the Heathrow to America airway that all of the passenger jets are flying in. So you can, if you notice, then you can see that all of this area here is Class A airspace. That means no VFR flight is allowed. You can only fly in here with an instrument rating, and you've got to have a clearance from air traffic control. And if you look here, we can also see that this is Class A airspace in this next to it, and this is 5,500 feet upwards. And then we've got, as we get a bit closer here to Heathrow, we've got Class A airspace here, 3,500 feet upwards. Now, it's not all Class A airspace. Let's go down a bit to Bournemouth. Bournemouth is a friendly place for us. We won't We'll put Southampton off the map because Southampton is the air traffic controllers at Southampton are strange. They go on a special anti-GA course, the air traffic controllers at Southampton, and they make life a misery. But Bournemouth, the air traffic controllers at Bournemouth, very lovely, very friendly, want to talk to us. And you'll notice that Bournemouth's airspace is quite complicated. Though. Can you see how you've got this Class A here? Can you see it says Class A here? Flight level 135 and upwards is all Class A. You can see here. And this square here is flight level 95 upwards, Class A airspace. But then sitting underneath it, this Class A airspace, is Bournemouth's controls zone. And this is Class D airspace, surface to 2,000 feet. And you'll notice that there's two parts to it. You see how you've got a little extendy bit here. So you've got like 2,000 to 5,500 feet is this little bit here. And that's Class D. And here you've got surface to 2,000. So you could probably work this one out, couldn't you? You can see that, well, hang about, you've got surface to 2,000 is Class D. You've got another bit which is 2,000 to 5,500 foot is this little bit here. So could you actually overfly Bournemouth, do you reckon, without talking to somebody on the radio?
Yes.
Yes, but you'd have to be very careful, wouldn't you, what height you were, because you'd have to be over 5,500 foot, but under flight level 135, wouldn't you? So, but of course, in reality, when you're flying around the UK, you always want to be talking to somebody on the radio. So you would probably be talking to Bournemouth. How would you know the frequency to talk to, though? Well, if you have a look, can you see it says here that lower airspace radar service is on 119.475. You've got the Class D control zone is controlled by Bournemouth Control Zone, Bournemouth Control 119.475. And you've got the Solent seat control area is on Solent control 120.230. So you've got marked on the map all these useful frequencies of the people you need to chat to actually find out if you can penetrate their airspace. And you can see that there's lots of there's lots of different ones that you've got. Southampton, you could quickly move on from Southampton. Don't ever try to talk to Southampton, you'll be wasting your time. But we've got all these other airspace. You've got Gatwick, you'll notice, is Class D, which is quite remarkable. In actual fact, you can fly through the Gatwick zone and you can actually fly over the top of Gatwick relatively easily in a light aircraft if you get the clearance and sound a bit like you know what you're doing on the radio. They'll give you a clearance right through Gatwick zone. And you see it's Class D. So VFR flight is possible in the Gatwick zone. You just need to talk to them on the radio. Heathrow, of course, as you probably imagine, is out of bounds because it's not just out of bounds because you've got Heathrow and it's all Class A airspace, but it's also out of bounds because of all of the other things we don't discuss in the nav course. You've got the fly clear rule and all those other things in air law that we talked about, and it's not possible to maintain fly clear and all sorts of things over the top of Heathrow. So obviously, if we were planning a flight, we'd want to look at all this airspace very carefully and work out exactly what height we can fly at. And of course, we'd have to work out our climbs and descents to make sure that we stay clear of the controlled airspace. Now, sometimes you might choose to deliberately go into these controlled airspaces. So, for example, if you're heading to the 2K, for example, which is a very popular destination, which is just over here in France, just on the coast here in France. If you're heading over to the 2K, you don't really want to be spending all this time over the channel out of radio contact, not talking to somebody. So you might well choose, for example, what I do, and a lot of pilots do, is I flight plan to go through the Gatwick zone. So I flight plan to, because it is more or less en route anyway, and I just get a clearance through the Gatwick zone, and that means I've got a nice, responsible air traffic controller with me on their radar screen going all the way to the 2K. So if I get a problem, somebody there knows who I am, where I'm going, and if suddenly my transponder goes red with a little red circle round it going bleep 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 bleep, they will know who I am and immediately try to contact me. So that's the different types of airspace. Now, let's go back and talk about latitude and longitude. So remember, Nick, lines of latitude, how do we note a line of latitude? What does it go from and to?
If the ones that go from 0 to 90.
Yes, it goes 0 to 90 north or 0 to 90 south. Yeah. And Danny, lines of longitude, how are they denoted?
Well, it's got like around the circumference.
Yeah. So they're lines that's going, these lines, aren't they?
Yeah.
And they go 0 to
60.
what? What do they go up to?
60.
0 to 60? Any advance on 60?
180.
Yeah, they go 0 to 180. In other words, all the way around to the other side of the globe, starting off from the Greenwich Meridian. And that means that everything east of the Greenwich Meridian goes 0 to 180 degrees east, and everything west of the Greenwich Meridian goes 0 to 180 degrees west. So, of course, that actually means flying in the UK can be particularly more difficult because it's complicated. Unfortunately, because the Greenwich Observatory was made the centre of navigation, we have a unique problem in the UK that you don't have in very few other places in the world. And that's basically that if I just bring up the chart and I'll zoom in on lines of longitude. So can you see that we've got here, this is a line of longitude, and this is 1 degree west. And then this is 2 degrees west. And then if we scroll along here, we've got 0 degrees, but then we've got another line here, which is 1 degree east. So that means that in the UK, 1 degree doesn't uniquely identify where you are. If you 1 degree, you could be here on this 1 degree, or you could be here on this 1 degree. So you've got to make very sure that you're dealing in east and west. And also, unlike places like the US, where everything is going in the right direction, you'll notice that if I'm here flying in this area, that the lines of longitude, my longitude value, increases as I head east, and it gets bigger and bigger as I head east. But if I'm flying in this area, my lines of longitude get less. So you can imagine the potential of getting a huge cock up is quite high in the UK. And I'm not going to be hypocritical and say I've never got it wrong. It is possible to get these things wrong. If you just look at a map, for example, and just look at a little bit here, if I'm just trying to find the latitude and longitude of somewhere, and I'm trying to count how far it is away, you've got to be very careful that which way you're counting. In other words, am I counting down from here, or am I counting up from here? And that depends on whether you're the east or west of the 0 degree line, which is here. So luckily, though, lines of latitude are much more straightforward. If we look at the lines of latitude, you see this is 53 degrees, runs all the way across the UK there. This is 52 degrees, runs all the way across there. Now, when we're specifying latitude and longitude, we always start with the latitude. So we're always going to look at how far up or down we are on the chart. So first off, we know that we're north. So if we wanted to find out the location of, let's just pick a random spot, shall we? There we go. There's something nice. Let's find out where Old Buckingham is. That's quite a nice little place. I've been there a few times. Old Buckingham Airport. So you'll notice that Old Buckingham is on the line of latitude here, and this is on this line of latitude here, and that is midway between 52 and 53. So we know that Old Buckingham is halfway between 52 and 53. So let's write that on the board. So I would write north, because we know it's north, 52 degrees. Now it's halfway, so that means it's 30 minutes. So let's find out where it is east-west, shall we? Which is obviously going to be a lot harder for us. So there's Old Buckingham. So the first thing we do is we've got to find out if it's east or west of 0 degrees. So there's 0. So we know that it's 1 degree east is this big line here. Yeah. So 1 degree east is that is there. So we know that it's 1 degree east. But how much east is it? Well, you can probably see if I look up here, that's that distance there. Here we go. So this is going to be 1, 2, 3, about 3 minutes. Yeah, so that's 4, 5, that's 10, that's 20, there's 30. So that's going to be 3 minutes. Yeah. So we would write that down. That's 1 degree east and 3 minutes. So that would be east 001 degrees. Three minutes. That's how we'd write down the latitude and longitude of Old Buckingham. So a couple of things to notice here is that obviously it's always in that sequence. You'll notice I put north and east. So there should always be a north or a south or an east and a west. You'll notice that the bit that goes north or south is 2 digits. And the bit that goes east-west is always 3 digits. The other significant thing is that the minutes here go 0 to 60. And then the fractional part of the minute is decimal 0. Or it could be decimal 1 or it could be anything. Yeah. So I'm always dealing in degrees and minutes, but the minutes are decimal minutes. We don't use seconds, the old-fashioned sort of mariner minutes and seconds. We now use decimal minutes. So this is the decimal. This is the decimal. Now the other thing to note is that when we're reading back positions in latitude and longitude, we actually use the word north, south, east and west. We don't use November echo. It's one of the few times when we use the phonetic alphabet, we actually use the real word. So I would read this position back as November 52 degrees 30.0 east 00103.0. Yep. That's how we'd read that back to air traffic control. So once again, it might work the other way round. You might be given a position that you've then got to mark on the chart. So the same rule happens, is that you'd have to look at your north, south, east or west, and then you'd find it on the chart. So what we would do is we would then, if you were given a latitude and longitude, you would find it along the top here. So if I was going to fly to somewhere that was, I've been told to fly to somewhere that was 5 degrees west, for example, and 52 degrees north, 0000 for both of them, I'd find my, I'd start off here with my 52 north, and I'd say, oh, there we go. And I'd find my 1 degree, my 5 degrees west, and I'd find out where the two intersect, which is going to be just there. And I'd be saying, there we go. That's where we'll be going, just there, Fishguard. But as a ferry heads off from Fishguard, heads off to Rosslare Island. And it's right next to the a nice VOR with a DME. So it's dead easy to get to, because the latitude and longitude are such that you can put it in your GPS very easily, and it's a very easy port to find. So that's an excellent waypoint if ever you're flying off to Ireland. And you'll notice that it's actually quite a short crossing from here to there. So that's how we show a latitude and longitude. So any questions on chart work, because we're going to move on to compass theory. Right, let's push on with compass theory. Now, we've talked about true north. True north, Vinny, is what?
Is that where north actually is in relation to the Earth?
Yeah, true north is the point the Earth spins around. Yeah, it's the bit where the pin sticks in the planet and it spins around that pin. Yep, that is the location of true north. But true north is not where the compasses point. So inside the Earth, there's lots of molten iron inside the Earth, and iron being ferromagnetic, as the Earth spins round, it creates an electric field, and that creates as a giant electromagnet. So if you can imagine it inside the Earth as a giant electromagnet. Now unfortunately, the electromagnet of the Earth isn't aligned with the point the Earth spins round. I know, sod's law. Well, you know, you win some, you lose some, don't you? So true north is actually here. It's actually in between Russia and America, and it's kind of in the middle of the sea. It's just there, true north. Now, so not only does it, sorry, magnetic north, I said true north. No, that's where the magnets point, just there. Now, the issue is not that the magnets point to this place where the Earth isn't spinning around, but it also changes all the time. So magnetic north constantly moves around the top of the globe here. So at the moment it's here, and it heads off in this direction. So every year it moves a little bit here, a little bit here, a little bit here, and after about 100 years it will finish up back to where it started, and it just constantly moves around. So the position where the true north is and where all of our compasses point changes as well as not being aligned to true north. So I'm going to bring up a nice little picture of that. Here we go. So you can actually see that here's the true north on the axis of rotation of the Earth, and then inside the Earth you've got this giant magnet, if you like, and this point here is the magnetic north. This point here is magnetic south pole, and then lines of flux or lines of magnetic force emanate from the North Pole to the South Pole, like this. Do you remember your O-level physics when the science teacher poured all the iron filings on the bit of paper and tapped it, and you saw those patterns of the lines of flux? Well, that's what you see on the planet. Now, one of the things to notice is that these lines of magnetic force come out the top and go all the way around and go in the south here. But can you notice that they also are coming out here and going in here? So that means if we were on the Earth here, roughly where, say, the UK is, the lines of flux are not just going from north to south, they're also coming out the surface of the Earth. So in other words, they're not actually coming directly from north, they're actually coming out a bit of an angle, and they go all the way down here and they go in at a bit of an angle. So that means that if we had a magnet here, it wouldn't just point to true north, sorry, it wouldn't just point to magnetic north, it would also tilt slightly, because the lines of flux, these lines of magnetic force, are coming out the Earth, and then they're going at an angle, and then they're going all the way around here, and then going back in at an angle. So our magnet is going to be sitting at a very, very slight angle relative to the horizontal, and we call that dip. So there is dip associated with our magnet. In other words, if we got a compass, the compass would point to north, but instead of pointing just to north, it would also exhibit dip, and very, very slightly, the actual needle of the compass wouldn't be horizontal. It would be just inclined an incy-wincy tiny bit. And you can see here, it would be dipping down towards the magnetic North Pole, because it would be following these lines of flux. So it wouldn't actually sit horizontal on the surface of the Earth. So how does that affect us navigating? Well, it means that we're going to use a compass as our primary means of navigation. Aviation charts are made relative to true north. I mean, let's face it, it would be pretty stupid to design any sort of map or chart relative to magnetic north, wouldn't it? Because we've already said that every year magnetic north is moving. So nobody's going to be dopey enough to try and make a map that's relative to something that's constantly moving. So we make everything relative to true north. But that means that if we want to use our compass as a primary navigational tool for north, well, the compass can only find where magnetic north is, and magnetic north changes every year. So how on earth do we know what heading to fly through on our compass? Well, when we work out where we're going to fly, we work out where we're going to fly true. So if I was going to fly to the east, for example, I would fly 090 degrees, and I would put a T after it. And the T means true. That means I'm going to fly a true heading. Now, whenever we're talking about headings, we've always got to put a letter after them. You can probably already see that anything to do with navigation, and this isn't just true of aeroplanes, this is any form of navigation, you can't say a heading of 080 or 100, because unless you specify what that heading is relative to, it doesn't make any sense. So 090 degrees true, that means I would be heading east on the chart following an exact line of latitude. But we've already said that because the magnetic North Pole doesn't align with the true North Pole, it's going to be something different. And we call this difference variation. So variation is the difference between true north and magnetic north. And if I said, or I could find out that the variation for, say, where we were in the world at that particular time, if the variation was, say, 3 degrees, then that means that our 090 degrees true might in reality be 093 degrees magnetic. And I would put an M after it to mean magnetic. So I'm always looking for this T, or I'm looking for an M after it. So how on earth do we know what the variation is? Well, let's grab a nice chart. There we go. Right, so here's one I prepared earlier. Recognize it? There we go. Brand new chart of Cyprus. So you'll notice that we've got these rectangles here, and in the middle of each rectangle, there's Vinny, what was this again? You see where I've got this one with a little 5? What was that?
That's the maximum elevation within that box of the ground.
That's right. That's the MEF, and these are the lines of longitude and lines of latitude. And of course, the nice thing about Cyprus is that you'll see everything goes up in a nice sequence. So it goes 33 degrees, 34 degrees. That's 33 degrees, 15, 16. Sorry, 15. Oops. 20, 25, 30, 35, 40, 45. And then going up this way, you can see that it's going 45 minutes, and it gets 35, 35, 15. Yep. So how do we find out what the variation is on a Cyprus chart? Well, what you have to do is you look at the chart and okay, can you read what it says there? Have I got the right bit? No, I haven't. Sorry. Where am I? That's the bit I'm after, so I'm not looking at the camera. So can you see what that says there? Magnetic variation for 2,000 feet is approximately 3 degrees 30 over the entire area. And its annual rate of change is 2 minutes increase. So in other words, the variation for the whole of Cyprus is 3 degrees 30, but it was 3 degrees 30 at when? Well, let's have a quick look here. 3 degrees 30, March 2001. So it's gone 10 years since then at least. So it changes by 2 minutes. That's 20 minutes. So 20 minutes is about half a degree. So that means the magnetic, here we go. So magnetic variation for the year 2000 is 3 minutes 30. 10 years on, that's another 20. So that means we could probably say that the magnetic variation for the whole of Cyprus it's going to be about 4 degrees. Yeah. That's for Cyprus. Now, let's look at the UK. Now, in the UK, we've got something completely different because the UK being a much bigger area, has variation changes over the whole chart. So we have something called isogonals. And what happened there? Curious. There we go. So let's just zoom in on a little piece of the chart. Oh, fuck. Now, can you see there's a little dashed line here that's running up here, and it says 1.5 degrees west. Well, that's an isogonal, and that's showing you that everywhere along that line, the magnetic variation is 1.5 degrees west. And you can probably imagine that if I go round the chart here, you see there's another one here that says 0.5 degrees west. So that means everywhere on that line between there, that's 1.5. This dotted line here is half. So that means that roughly in the middle here, in this area here, between the two, there's the 1.5. That's the half. So this would be 1 degree west here. So in the UK, you have to find these isogonal lines, find out the one you're nearest to, and work out what your variation is, and it changes over the whole chart. Now in the UK, there's a special isogonal, and it's 0. You're very rare that you find a country that's got 0, and we call that the agonic line. In other words, the agonic line is the 0 degree isogonal. So you can imagine, like, there's some lots and lots of bloody questions now in the exam we're already up to, isn't there? Typical exam question is, what is an isogonal, or what is the agonic line, or what is variation? And there's loads of answers, things like variation is the point of equal magnetic deviation, and there's all sorts of like dodgy answers. You've got to be a bit careful. So how do we actually convert, once we know what the variation is, how do we actually convert from one to another? Okay. I'm going to start to introduce you to some exam tips now. Now, in the navigation exam, you'll be given a sheet of blank paper for rough working. Now, before you put pen to paper and before you've even read the exam paper, you've got to write some things on that rough working out sheet. One of the things that we write on the working out sheet is we write some letters. You write T, B, N, D, C, which is true virgins make dull company. And what all of these letters mean, what this true virgins make dull company is, this is true. This is variation. This is magnetic. This is deviation. And this is compass. So this TVMDC is showing you the meaning of the difference of the word variation and deviation. So you'll notice that variation sits between T and M, and deviation sits between M and C. So that means that variation is the difference between true and magnetic. Deviation is the difference between magnetic and what the compass is reading. So that's how you tell the difference between variation and deviation. And I can assure you that if you get this wrong, you'll piss the exam away. Because you'll probably throw away at least 2 questions. You've done the nav exam, haven't you, Vinny?
Yeah, I've done all my exams.
Yeah. How would you support that theory?
100%. It was a while ago since I've done them, but I did exactly as you advised there, is writing down a few things before, and I do remember doing exactly that.
Yeah. So just remember, true virgins make dull company. There's a couple of other things that you'll need to memorize for the exam, and I'm going to make a list of them just here on the board. And as we go on in there, I will build this up. So variation, difference between true and magnetic. Deviation is the difference between the magnetic and what the compass is reading. So the difference between magnetic and what the compass is reading we call deviation. And what is causing deviation? Well, deviation is caused by the aeroplane itself. So the aeroplane itself has got lots of magnetic inducing things in it. Notably that it's got bits of wire all over the aircraft that's creating a magnetic field. And the magnetic field that these wires produce cause an error in the compass. And we call this error deviation. So let's think about this. So variation is caused by what, Robbie? What causes variation?
So the difference between magnetic north moving over time and it changing from true north.
So
Variation.
the variation is the difference between true and magnetic. And is that affected by the aeroplane itself, Robbie?
No.
No, it's not. What causes variation? What is the number one thing that causes variation?
Time.
No, it's where you are on the planet. It's different for everywhere on the surface of the Earth. So variation is where you are. So in some places, variation can be as little, like in the UK, it can be 1 or anything between 0 and about 1.5 degrees. It can be very small. Other places I've flown at, for example, in South Africa, the variation is 25 degrees. So can you imagine if you're flying in South Africa and you get your variation a bit up the creek and you get adding and subtracting all wrong, you're going to be heading off 50 degrees wrong. Well, you set off from Cape Town, heading off across Namibia, across all that red featureless terrain, and you're 50 degrees wrong. Well, hey, you and I are going to have some problems very rapidly, I tell you. You'll be making friends with lots of springboks and zebras that's come to sniff your aeroplane as you've landed in the middle of nowhere with your mobile phone not in service and dodgy things happening. So variation is a function of where you are on the planet. Deviation, Danny, what is deviation and what determines it?
Deviation is like the impact your aircraft has on the magnetic compass in the aircraft, and it's determined by the deviation card in the aircraft cockpit.
That's right. So deviation you would expect to be a function of the plane, wouldn't you? So if you got in, say, India Yankee or Charlie India, you'd expect the deviation to be different in each of the two planes, but you'd obviously expect the variation to be the same, wouldn't you? Because that would just be in Cyprus. And it's very important to realise the difference there. And you can imagine there's loads of exam questions you can be asked on this. So how do we use deviation? So and variation. Let's talk about that. So the way I do it is I draw arrows, and you can imagine there's an arrow going this way, and there's an arrow going this way, and I write on here W plus, because the arrow's going to the right. Now that means if I've written W plus, then logically it must be E minus. And then this arrow's coming this way, so that means that if it's coming this way, that it must be the opposite. So that's going to be W minus E plus. So how does that, what relevance is that? Okay, let's go back to our map of the UK, shall we? So over here, we've got an isogonal here, 1.5 degrees west. So if I'm flying around in Wales, that I'm going to be having a variation of 1 degree west. So we've got variation is 1 degree west. So I could probably have my plog and I would probably somehow write on it somewhere that it's 1 degree west, because I would get that off the chart, wouldn't I? So I want to fly. I want to draw a line on my chart. I find out exactly east, and it's 090 degrees. True. What is that magnetic? Okay, so I want to now work out what that is magnetic. So that means I want to go true to magnetic. So let's go back to our little diagram here. I want to go true to magnetic. So if I want to go in that direction, I've got to find the arrow going in that direction. So true to magnetic is the arrow going here. So the arrow going there has already said this 1 degree west. I've got to add west to go true to magnetic. So I've got to add the west. So that means that that's 091 degrees magnetic. So supposing, let's do another example. Supposing it was 172 degrees magnetic, and I want to find out what it is true. So, Robbie, how would I go about that, do you think? I want to go from magnetic to true.
So you would subtract the 1 degree west because you're going to the left.
So in other words, I'm going magnetic to true. So this is the arrow I'm looking at. Yeah, I'm going in that direction. And it says here, I subtract off west. So the variation is 1 degree west. So I have to subtract off west, as you quite rightly point out, which means it's 171 degrees true. So who's next? Nick. I didn't notice you'd sneak in there, Nick. You must have sneaked in while I wasn't looking. So supposing though we've got the variation is 1 degree west, and supposing it's the deviation is 3 degrees east. Let's go back to our original example here. 090 degrees true, 091 degrees magnetic. I want to find out what I have to steer on the compass. So Nick, how am I going to work out this? How do I convert magnetic to compass?
Because you're going right, you'll be adding west, minusing east. So if it's 3 degrees east, you're minusing it off, so it'll be 087.
Is it 087?
Oh, we go from 090 or from 091?
Now remember, we're not going true to compass.
Oh, we go from magnetic. We go from magnetic. Oh yeah, so 88.
Yes. So you'll notice that on every single time I've ever written degrees down, I've either written T, M, or C. In other words, true is what it is on the chart. Magnetic is what it is relative to magnetic north, and 088 is what I have to steer in the aircraft on the compass. And remember, although I've shown them as, we're doing this example as 1 degree because we've just picked that off the UK chart, this could be huge. I mean, there's places in the earth, particularly right up in Greenland, for example, where this can be so much that you can't, it can be like 60 degrees, and it's kind of hardly worth using the damn compass. Some sort of like magnetic automatic get you lost device. So this is how we're going from magnetic true to compass. Now, of course, bearing in mind that you've always, if you're going true to compass or compass to true, you've always got to go via the M. Yeah. You can't go T to C or C to T. You can only go C to M, M to T, T to M, M to C. Yep. Because you have to apply variation to go T and M, deviation to go M and C. There's no such thing as variation deviation, yeah? Because one is where you are on the planet, one is the plane you're flying in. So how do we know what, we've talked about variation. We know that we can get the variation from the chart. So how do we know what the deviation is for a particular aircraft we're flying? Well, every time a plane goes in for its certificate of airworthiness, some guy has to take the plane to a special point on the ground where you can guarantee there's no electric cables and things. And they align the plane very, very precisely with magnetic north, or with north. They can work out where magnetic north is, because bearing in mind that they can work out what the variation is for that particular point and that particular time of year. And they turn everything on in the plane, they start the engine, turn everything on, and they find out exactly what the compass is reading for each of these various points. And they turn the plane through, it's not scientifically, you just literally, you turn the plane by just getting the nose wheel and you just shunt it around into another exact bit. In other words, you've got this big cross on the ground with a 0, 45, 90, all shown at various points, and you just align the plane very, very precisely on these points on the ground. You just literally look at the compass and you see what it reads. So that means that you have a series of points on the ground, and you would say, right, well, I've turned the plane onto in other words, magnetic, and the plane's compass is actually read 002. And then you would then say, right, and then at 0, maybe 4 or 5 degrees magnetic, the plane's compass read 040 degrees compass. And you could imagine that you would have a little chart, couldn't you? A little card that would just have sort of 4 or 8 points on it, showing you what the difference is for various bits. And this would be showing you the deviation. And we call this the deviation card. And the deviation card is The deviation code is I'll have to do a small modification here. So this is my aeroplane. Okay, that's the compass that sits on sitting on the top of the plane. Yeah, on the top of the dashboard here. And what you find is that underneath the compass here, there's a small, just a very small bit of paper. I mean, it's only literally that big and it's that high. It's just a tiny, weeny slip of paper, and we call this the deviation card. And so you could look at that, couldn't you? And you could convert magnetic to compass by just looking at that deviation card. It's just sitting underneath the compass. Obviously, when they made this big hole here, that was the somebody nicked the compass. So we talked about a variation. We've talked about how to find it on various charts. Now let's look at a VOR here. Now I've chosen Torbay VOR because it's quite a nice Torbay VOR. Because Torbay VOR aligns with it's more or less actually on an exact line of longitude. So can you see, this is the Torbay VOR. Once again, it's ident is Bravo Hotel Delta, which is Brixham. It's frequency 112.05. It's also got co-located DME, distance measuring equipment, in it. Now, this circle around it is showing you small compass rose. And VORs tell you where you are relative to them, but they are aligned to magnetic north. They're not aligned to true north, they're aligned to magnetic north. And you can see that from this particular one. Can you see how this arrow from the VOR, you can see is actually a very, very slight angle off north-south. And the difference between the true north, which is obviously this line of longitude, and this arrow here, is actually the variation. And we've already said that the variation in this area is about 2 degrees. So the difference between that arrow and this straight line is going to be 2 degrees. So as another way of navigating, you could actually use this VOR compass rose, couldn't you, to actually find a magnetic heading from any point to any point. But we don't, because we always are working in true. Everything we do, all the calculations, all the plots, all the navigation we do, the GPS equipment in your aircraft, everything we do is true. Now, the reason why VORs are magnetic is because years and years ago, of course, planes didn't have any equipment that could deal with trues, and true was quite a bit more complicated. And it wasn't until 1984 did the world agree even where the true north actually was. So you tend to find that VORs are actually aligned to magnetic north, not to true north. And the answer to your next question is yes, they do have to be adjusted. Every year, somebody has to tweak them a little bit and move them, you know, a couple of move the transmitting device around a centimetre or whatever, a fraction of a degree, to keep them perfectly aligned to magnetic north, because magnetic north changes. So there's exam questions on that. What is, you can probably imagine, VORs are aligned to, and the typical answers will be magnetic north, grid north, true north, or agonic north. And obviously the answer is magnetic north. And there's no such, and all the others, it's not true north, and the other two norths are just cobblers. So what affects the compass as well? Well, we've already said that the we've got a deviation card. Let me just bring up a deviation card, because I'm pretty sure I've got a nice one here somewhere, have I? Slide number, yes, I know, Pooley slide number 20 has got a picture of a deviation card in it. Let me just bring up slide number 20. Here we go. There we go. This is the so you can see here that how the plane was put on the ground, and we've got a little card that just sits below the compass, and it says, well, this one says electrical services off, electrical services on. I've never come across a deviation card ever that says everything turned off, because that's a fat lot of good in a plane, isn't it? But you could see that you've got a little thing here that says, for magnetic, steer these, and it shows you what the differences are. Right, so what affects it? Well, when you get in the plane next, just before you start the plane, just take your mobile phone out your pocket and put it on the top of the instrument cowling, on the coaming there, and you'll get a shock. What happens to the compass? And yes, people have got themselves lost severely because their phone's rung in flight. They've answered it and they've just put it on top of the dashboard. And wow, does it cause a problem? So you've got to think about these things when you're flying a plane. The things like headsets, mobile phones put near the compass will have a very dramatic effect. Right, now I need to talk about, I'm sorry guys, I need to talk about something else. So it's part of the syllabus and sometimes exam questions on it. And it's the most crappiest bit of the entire PPL syllabus. Of all the 9 subjects we cover, there's one bit that's really, really shitty. And this is the bit I need to cover. So we'll just get it out the way, shall we? I'm going to talk about compass errors. So we've talked about variation and we've talked about deviation. So deviation is the difference between magnetic and the compass based on magnetic interference from the aircraft itself. Now there is another thing that causes compasses to go up the creek. Now, whatever you do, don't try and study what I'm about to tell you, because all the books are wrong. You know, everything you read on the internet is wrong, because nobody understands what actually is the real issue. And I'm going to talk about acceleration and turning errors. Now, acceleration and turning errors are extremely complex bits of physics that's going on. And the books try to explain them by central gravities and forces and weights and all sorts of crap. In reality, it's caused by physical things moving in electrical fields that create secondary effects. But it's all way too complicated. Even at ATPL level, we don't talk about it because it is just mind-blowingly difficult to get your head around. So I'm going to talk about what actually happens and what we do about it. I'm not going to go into the physics and all the bollocks that relates to it all. You'll just have to accept the fact that there are some magical things that happen to magnets. Now, the first thing that happens is what we call a turning error. Now, what a turning error is that if I get an aeroplane, it doesn't have to be an aeroplane, it could be anything. Boats, could be a boat, a rowboat, a yacht, it could be a car, doesn't matter. And I have a compass, and I turn the compass, and I'm holding this compass. I just move it around like this, and I'm just move it around in circles, and I move at an exact constant speed. You would expect the compass to turn at exactly the speed that I was turning by, wouldn't you? But life is not that straightforward, and it doesn't. If I stop at any point, the compass there'll be a slight delay, and the compass will find the exact place I'm going. So in other words, I could move it here, and and then the compass will move to that exact spot. And as I move around, the compass will be turning, but it won't quite be turning in synchronization with myself. And we call this a turning error. And there's a magic thing you have to remember. Magic mnemonic. And it's UNOS. And I'm going to write it over here on the board because this is another word you've got to write down for your navigation. And what UNOS is, it's undershoot north, overshoot What that means is if I want to turn onto north using my compass, what I have to do is I have to undershoot it. In other words, I have to stop before I get to north. And what will happen is, as I stop before I get to north, the compass will move about another 15 degrees. And then it will go ding and read north. So in other words, if I was turning onto north, I would go 330, 340, 350, stop on 350, and the compass would carry on and it would read 360. So if I was turning onto north, I would have to undershoot. If I was trying to turn onto south, I would have to overshoot. In other words, if I was holding the same compass, now I wanted to turn onto south, I would go 160, 170, 180, 190, stop, and then the compass would go 190, yeah, and it'd go back to 180. And we call this a turning error. And this is all you need to know is if you're turning onto north, you have to undershoot. If you're turning onto south, you have to overshoot. If you're turning onto east-west, you're fine. There isn't a turning error on east or west. In other words, if you wanted to turn onto east or west, you just grab your compass, wherever it's showing, here we go, 080, 090, stop. And the compass will stay at 090. If I then want to turn on to 270, I'd start turning. I'd hold my compass, here we go, 250, 260, 270, stop. And the compass would continue reading 270. In other words, there wouldn't be a turning error. So you can imagine there's exam questions will say turning onto 090, what would you undershoot, overshoot, or stop on the right heading? And of course, you would look here because you'd written this down, UNOS, and you would say, aha, I undershoot north, I overshoot south. That means if I'm turning onto east, I don't do anything. I just turn onto east and it will stay on east. That's all you need to know about turning errors. Just accept what I'm saying. Don't, whatever you do, have a good idea and try and read the book. And whatever you do, don't try and research this on the internet because it will just confuse you. And the book is all bollocks, and most of the stuff you read on the internet is based on the books, and all the books are all various shades of grey of bollocksness as well. Right, the next thing we talk about on errors is what we call acceleration and deceleration errors. Acceleration and deceleration errors. Now, what an acceleration or deceleration error is if I get a compass, and I mean, this is once again, this isn't an aeroplane problem. This is, you get the same problem in a car, in a boat, on your push bike, or even just holding a compass in your hand and you're just walking along with it. You get this problem. Is that if I take the compass and I just move it like this, in other words, I accelerate it or I decelerate it. In other words, I accelerate it like this, and then I can decelerate it and bring it to a halt. Or if I'm walking along with it and I just stop, the compass will actually turn. It will only turn for a short fraction of a time, but it will turn and then it will go back again to what it was. And we call that an acceleration or deceleration error. Once again, there is a mnemonic, and the mnemonic is ANDS. So what this is saying is if I accelerate, I will get a turn to the north. If I decelerate, I will get a turn to the south. So that means if I'm got my compass showing 090 and I move it, I get a turn to the north. So that means my compass is going to go 090, 080, stop, back to 08, back to 090. And once again, I take my same compass and it's showing 270. If I accelerate it, it shows a turn to north, so it's going to show 280. And as I stop, it moves back to 270. If I decelerate, it produces a turn to the south. So if I'm walking along with this compass on 270 and I'm maintaining 270 and I suddenly stop, my compass produces a turn to the south and it will show me 260. And then it will go back to 270 again. So that's another thing I need to write down here is ANDS. So we've got TVMDC, UNOS, and ANDS, okay? Now, the thing to notice with these acceleration, deceleration errors is that if I accelerate it, it produces me a turn to the north. In other words, this only happens if I'm east or west. So if I'm already on north, I can't, and I accelerate or decelerate, I can't get an extra turn to north. I mean, there's no such thing as a super north or a super south. So these acceleration, deceleration errors only happen obviously on an east or west heading. And just like a turning error is only happening on a north or south heading. Now, if I'm somewhere in the middle, like if I'm 045 magnetic, or sorry, 045 compass, then I will get roughly half of the error. Same with here. So in other words, if I'm not quite if I'm somewhere in the middle, I'll only get half the effect. And that's really all I want to talk about for compass errors. I don't want to go into any more because there's normally an exam question on it, but normally you'll only get one question. So it's not worth spending a lot of time on compass errors. But in the good old days, when you used to fly like tiger moths, you'd have a compass between your legs. Beautiful, fantastic compass it is, not like the crappy things they put in like aircraft nowadays. It's a big brass work of art that sits down on the floor. And of course, you'd have to fly on the compass. And the compass would actually have these turning errors and acceleration and deceleration errors that that I've been talking about. So why do we not see these on an aeroplane? Well, if you remember, what we do is we get the plane flying straight and level. So we're not accelerating, we're not decelerating, we're flying straight and level. We wait for the compass to be steady, and then we set the DI to the compass, don't we? We twiddle the DI so it reads exactly the same as the compass. And the DI is a gyroscopically controlled instrument. The DI isn't interacting in any way with the magnetic north of the Earth. All it's doing is showing you, it's just an instrument that's showing you where you are from when you set it last. So in other words, we use the gyroscopically based instrument to turn onto, because the DI, being a gyro, doesn't suffer from turning errors and acceleration or deceleration errors. That's why we have a DI, we don't have a compass, because we had a compass there, it would suffer from turning errors, acceleration errors, and deceleration errors. I mean, if a compass didn't have all these problems, we probably would never have invented the DI, the directional indicator. We'd have probably just had a very sophisticated kind of compass here with gears and things in it to do it. But compasses are such a pain in the arse to use for flying. That's why they developed this gyroscopically based instrument. And what we have to do is in flight is sort of every 10-15 minutes, we would just get the plane flying nice, straight and level, look at the compass, there it is, 046, and you go 046, or in this case, 3, this is 315, 314, so you go 314, there we go, twiddle, twiddle, there we go, 314 degrees.